Hello and welcome. Today we are talking about high performance computing, or HPC, and the related challenges faced by the current storage solutions. In a typical HPC environment, you'll find a wide range of software that differ in storage I/O requirements. For example, supercomputers, AI, and oil and gas exploration all generate huge data volumes, and the ultimate challenge is to achieve high bandwidth, IOPS, and ultra-low latency within a single storage cluster. Needless to say, the current challenges lie in the disparities between bandwidth and IOPS-intensive services, which all have different performance metrics, software stack scheduling policies, and optimal media access models. Consider the various metrics that are needed to measure the performance. For example, IOPS-intensive services are centered on the total number of I/O requests processed per unit time and the processing latency of each I/O. In such services, requesting a large number of I/Os is frequent and needs to be quick. The primary challenge for storage is resolving the conflicts between CPU scheduling policies and queue management in hybrid load scenarios. Another issue is that of bottlenecks. The bottlenecks in IOPS-intensive services primarily arise from CPU computing power and software call stack depth. In this case, it is crucial to minimize the request amplification and depth of the I/O stack. The major challenge for storage lies in optimizing the processing logic of the software call stack to minimize bandwidth amplification while maintaining a lean software stack. Another area of focus is the optimal media access models. Bandwidth-intensive services require greater disk I/O, resulting in reduced metadata, improved disk LBA sequentiality, and higher performance. On the other hand, IOPS-intensive services require a higher match between I/O size and disk management granularity, as well as small I/O amplification. In this case, the storage challenge lies in accommodating both large and small I/O requirements in data layout. To tackle these challenges, the Huawei next-gen OceanFS parallel file system effectively balances both bandwidth and IOPS-intensive services thanks to a series of innovations. First, it uses the large I/O pass-through, high-ratio erasure coding, and copy integrated verification technologies to reduce network, disk, and memory bandwidth amplification. Additionally, the append-only disk layout enables sequential disk I/O access. Second, small I/O aggregation, new-gen distributed cluster technology, and one-sided RDMA address deep software stacks and CPU computing bottlenecks, achieving high IOPS and low latency. And last but not least, hybrid storage requirements are met using the key technologies like intelligent CPU scheduling, end-to-end QoS, and adaptive multi-granularity disk management. Let's take a look at these in a bit more detail. Traditional storage arrays write I/Os to memory, perform copy mirroring between controllers, and respond to services. For small I/Os, the shortest path is that with the lowest latency. However, copy mirroring doubles the network and memory bandwidths. As a result, the maximum service bandwidth can only be half of the network and memory bandwidth. Copy mirroring also causes the CPU service loads to double, which further deteriorates the CPU performance in small I/O scenarios. To mitigate the amplification in network and memory bandwidth, the intelligent caching feature aggregates file I/Os into large I/Os without making copies, and passes the large I/Os from clients to disks. For small I/Os that cannot be aggregated, the copy mirroring is implemented by the one-sided RDMA to further reduce the CPU overheads by 30%, without increasing the I/O stack depth, ensuring low latency and improving IOPS performance. To achieve load balancing and capacity balancing in scale-out storage, the system uses at least two layers of dispersion logics, which are metadata service dispersion logic and object storage dispersion logic. They are used to balance the metadata access loads and the use of storage capacity. To ensure excellent performance for hybrid loads, OceanFS uses the intelligent CPU grouping algorithm and end-to-end QoS to execute software stack scheduling policies that are adaptive to either large or small I/Os. Dynamic CPU grouping automatically separates large and small I/O request queues from CPU scheduling based on the characteristics of large and small I/Os. Here, I/Os are processed by dedicated cores to deliver higher bandwidth for large I/Os and low latency for small I/Os. Then each I/O is processed by a fixed CPU core. The processing does not require switchover or context weighting, reducing unnecessary system overheads. Finally, the system automatically identifies priorities, such as processing foreground I/Os before background I/Os, metadata before data operations, and responses before requests. Mainstream file systems manage disks through write-in-place, but this is prone to data fragmentation when the system is running for a long time. Bandwidth performance is hindered by this fragmentation, caused when files are repeatedly created and deleted, and large I/Os are split into multiple small I/Os. OceanFS introduces append-only data management that appends new data to continuous blank space. Invalid data is recycled in the background, and continuous disk space is released for large I/O continuity on disks. This mechanism provides a basic assurance for high bandwidth and IOPS write performance for hybrid loads. Disk bandwidth is high if the granularity of continuous disk I/Os is large. In the case that all large granularity indexes have been used, small I/Os are amplified several times when written, further deteriorating the performance and latency. This is where adaptive multi-granularity disk management comes in. OceanFS uses two-level indexes. Primary indexes have a fixed length and large granularity, delivering the read and write bandwidth for large I/Os, and sub-indexes have a variable length, which can automatically adapt to the size of each I/O to flexibly meet the read and write requirements. And that concludes this video. Thank you for watching, and I'll see you next time.